Have you ever wondered why salt is put on icy roads? Or why salt is used in the ice cream making process? And it's not to flavor the ice cream. The answer lies in something called a colligative property. And in this video, I'm going to explain to you what a colligative property is and one important component of a colligative property, and that is the Van Hoff factor. And we'll even go through some practice questions where I show you how to figure out or estimate the Van Hoff factor of a specific solution. So let's take a look at these four beakers. Beaker number 1 contains pure water. The second beaker contains a 1 mol solution of glucose. The third beaker contains a 1 mol solution of sodium chloride. And the fourth beaker contains a 1 mol solution of potassium phosphate. Now that we know what's in each beaker, let's take a look at the freezing point of each beaker. The freezing point of the first beaker is hopefully well known to you, and that is 0 degrees Celsius. Pure water has a freezing point of 0 degrees Celsius. But what happens when we make a solution? The second beaker contains that glucose solution, a 1 mol glucose solution. The freezing point of that solution is negative 1.86 degrees Celsius. So something happened here. We added glucose to the water, and the solution now has a lower freezing point. Let's take a look at the sodium chloride solution. So we have a 1 mol solution of sodium chloride, and it has a freezing point of negative 3.72 degrees Celsius. And the last beaker has a 1 mol solution of potassium phosphate, and it has a freezing point of negative 7.44 degrees Celsius. So before we go any further with this, let's take a look at what is happening when each of these substances dissolves. So the first one, where we have a component dissolving, a solute dissolving in the water, is our glucose solution. Let's first zoom in and write out what is actually happening when glucose dissolves in water. So for every 1 mole of glucose solid that dissolves, it's going to create 1 mole of aqueous glucose. It's a 1-to-1 ratio. And because this is a covalent compound, or it creates molecules in solution, it's not creating ions. So it's going to be a non-electrolyte, meaning it doesn't allow electricity to be conducted through it. Now let's contrast this to our sodium chloride solution. Now sodium chloride is an ionic compound, and when it dissolves, it's going to create ions in solution. It will create an electrolyte solution. Now we're going to assume that it's completely 100% soluble, and for every 1 mole of sodium chloride solid that dissolves, it's going to create 1 mole of sodium ions in solution and 1 mole of aqueous chloride ions, giving us a total of 2 particles in solution for every 1 particle that dissolved. Now let's take a look at the last example, which is our potassium phosphate. We're going to assume that it will completely 100% dissolve. So for every 1 mole of solid potassium phosphate that dissolves, we're actually going to get 3 moles of potassium ions and 1 mole of a phosphate ion in solution, giving us a total of 4 particles in solution for every 1 particle that dissolved initially. I want you to take a look at the freezing point of each of these solutions and the number of particles that I drew in the beakers. Now, can you see that relationship between the freezing point and the number of particles in solution? Well, that will help us define a colligative property. Now, colligative property is a property of a solution that depends only on the number of particles in that solution and not the identity of the particles in that solution. So let's go through an example of what I mean by this. So sodium chloride, if we have a 1 mol solution of sodium chloride, we know we have 2 particles in solution for every 1 particle that dissolved. Okay, the sodium ion and the chloride ion. And we also know that the freezing point of this solution is negative 3.72 degrees Celsius. What if we have a 1 mol solution of potassium chloride? What will its freezing point be? Well, hopefully you guessed it. Potassium chloride will dissolve into potassium ions and chloride ions, giving us a freezing point identical to the sodium chloride solution. Because remember, it doesn't matter what is dissolving. It just matters how many particles you have in that solution. And this number of particles is so important that it actually has a name, and that is called the Van Hoff factor. And it will actually help us later on to make calculations regarding freezing point and boiling point and some of the other colligative properties. So let's go through the Van Hoff factor of each of these solutions. Now, the glucose solution. Now remember, 1 mole of solid glucose that dissolves will create 1 mole of aqueous glucose. So the Van Hoff factor for that glucose solution is 1. The sodium chloride, 1 mole of sodium chloride that dissolves will actually create 1 mole of sodium ions and 1 mole of chloride ions, giving us a Van Hoff factor of 2. The last one is the potassium phosphate. 1 mole of potassium phosphate that dissolves will actually create 3 moles of potassium ions and 1 mole of phosphate ions, giving us a Van Hoff factor of 4. Now this Van Hoff factor is only an approximation, and really what happens when you dissolve something in water is it doesn't always fully 100% dissolve. So we're doing the best at making this approximation. We should recognize that it is just an approximation of how many ions will be in that solution. So now let's do some practice trying to identify and determine the Van Hoff factor of these 4 solutions. I want you to pause the video and try these 4 on your own. So let's start with the lithium chloride solution. Lithium chloride is an ionic compound, and when it dissolves, it will separate into lithium ions and chloride ions. So for every 1 mole of lithium chloride that dissolves, you'll get 1 mole of lithium ions in solution and 1 mole of chloride ions in solution. This will create an electrolyte and have a Van Hoff factor of 2. The next one is carbon dioxide. Every time that you drink soda, you're drinking a solution of carbon dioxide and sugar in water, mostly. Now, carbon dioxide is a covalent compound. It's molecular. So when carbon dioxide dissolves, it's not going to separate into individual ions, and it's not going to create an electrolyte solution. So for every 1 mole of carbon dioxide gas that dissolves, you're going to get 1 mole of carbon dioxide in aqueous solution. So that means our Van Hoff factor for carbon dioxide is 1. The next one is magnesium chloride. So magnesium chloride is an ionic compound, and when magnesium chloride dissolves, if it completely dissolves in solution, it's going to create 1 magnesium ion and 2 chloride ions, giving us a Van Hoff factor of 3. The last one is our 0.1 molar solution of sucrose. So this is C12H22O11. This is definitely a covalent compound, and when it breaks apart, it's not going to create individual ions. It's going to create dissolved molecules of sucrose. So for every 1 mole of sucrose that is dissolved, it's going to create 1 mole of aqueous sucrose, giving this a Van Hoff factor of 1. In this video, I'm making a huge assumption that all of these substances are 100% dissolvable, and that's not always the case. So keep that in the back of your mind when you're doing these estimations. Another thing to keep in mind is that sometimes when you're using equations, you will see this lowercase letter I. That is often the representation or the symbol for the Van Hoff factor.